Right now, as you sit in your chair, you are hurtling through the cosmos at speeds that would make a jet fighter seem motionless. You're not just spinning with Earth's rotation at 1,000 miles per hour. You're not simply orbiting the Sun at 67,000 miles per hour. You are rocketing through space at over 560,000 miles per hour aboard a cosmic island so vast that light itself, travelling at 186,000 miles per second, takes 100,000 years to cross from one edge to the other. This is your home. This is the Milky Way galaxy. And tonight, we will embark on a journey that will forever change how you see your place in the universe. Astronauts often describe a moment that changes them forever, the first time they peer through their spacecraft window and search for home. Cities that seemed enormous from ground level appear as scattered pinpricks of light. Mountain ranges that took hours to drive across now stretch beneath them like wrinkled paper. They squint at the surface below, hoping to spot their hometown, their street, maybe even their own backyard. But here's what shocks them most. They cannot see their house. They cannot see any house. From just 250 miles above Earth, individual buildings vanish completely. The resolution of human vision simply cannot capture objects that small from that distance. This reveals something profound about scale that we rarely consider. Distance erases detail. From the International Space Station, entire neighborhoods disappear. Cities become fuzzy patches. Countries blend into brown and green smears across the planet's surface. What seemed impossibly large from ground level proves impossibly small from space. Now imagine pulling back further. At 1,000 miles up, entire states fade into indistinct shapes. At 10,000 miles, continents start merging into a blue marble floating in darkness. The Earth that felt infinite when you walked across your backyard now fits comfortably in your field of view. This perspective trick works both ways though. Just as we shrink when viewed from above, the space around us grows more vast than our minds can grasp. That empty blackness surrounding our tiny planet stretches in every direction for distances that make the width of Earth seem like a grain of sand on an endless beach. Consider this. If you could somehow shrink Earth down to the size of a marble sitting on your desk, the nearest star would still be over 4,000 miles away. That marble would sit alone in an empty space, stretching farther than the distance from New York to Los Angeles. The isolation is staggering. This crushing emptiness between objects defines our cosmic neighborhood. We exist on a tiny rock surrounded by an ocean of vacuum so vast that light, traveling at 670 million miles per hour, takes years to cross from one point of interest to the next. But we are not alone in this emptiness. We travel through it as passengers on something far grander than a single planet. We ride aboard a collection of stars and worlds so enormous that it dwarfs our wildest imagination. We inhabit a galaxy. However, there is a catch. Just like astronauts cannot see their own houses from orbit, we face an even stranger problem when trying to comprehend our galactic home. We live inside the thing we are trying to study. The photons illuminating this moment began a journey that makes every human exploration look like a stroll around the block. Light from our nearest stellar neighbour, Proxima Centauri, left that star over 4 years ago. 4 years. The light hitting your eyes right now began its journey when different people held different jobs, when different songs played on the radio, when the world looked completely different than it does today. This light travelled through the vacuum of space for 4 years to reach you in this moment. Columbus sailed approximately 4,000 miles from Spain to the Americas. That seemed like an impossible distance to his contemporaries. They worried he might fall off the edge of the world. They feared sea monsters and endless storms. 4,000 miles represented the absolute limit of human courage and imagination in his time. The light in your room travelled 25 trillion miles. Let that number settle in your mind. 25 trillion miles. If you could drive a car at highway speed for 24 hours a day, 7 days a week, without stopping for gas or food or sleep, it would take you over 40 million years to cover that distance. 40 million years of non-stop driving just to reach our closest stellar neighbour. This reveals the true scale of our galactic neighbourhood. Stars that appear as tiny pinpricks of light in our night sky actually shine as massive nuclear furnaces, many larger and brighter than our own Sun. They look small only because of the breathtaking distances involved. Space stretches so far between stars that light, the fastest thing in the universe, requires years to make the crossing. Our galaxy contains roughly 400 billion of these distant suns. Some shine just 4 light-years away like Proxima Centauri. Others blaze from distances of 50,000 light-years or more. Each one pumps photons into space, sending light racing across the void toward us. Some of that ancient starlight left its source before humans existed. Some began its journey before dinosaurs walked the Earth. When you look up at the night sky, you see a time machine. You witness the past broadcasting itself across space. The stars you observe might have exploded centuries ago, but their final light still travels toward you, carrying messages from a cosmos that no longer exists. This creates a strange situation. We live inside something so vast that we can never see it all at once. We experience our galaxy like ants crawling across the surface of a giant clock, able to examine tiny portions, but never able to step back and witness the complete mechanism. The light from the far edge of our galaxy has been travelling toward us for 100,000 years, carrying information about places so distant they might as well exist in a different universe entirely. Imagine holding a single grain of sand between your fingers. Feel its tiny weight. Notice how it barely registers against your skin. This grain measures roughly 1 millimeter across. You could lose it in the carpet and never find it again. You could blow it away with a gentle breath. It represents one of the smallest objects you can comfortably handle with your bare hands. Now let this grain of sand represent the entire Earth. Every mountain, every ocean, every city, every person who has ever lived gets compressed into this tiny speck. A whole world shrinks down to something you could accidentally inhale. On this scale, what size would your city be? Your neighborhood becomes invisible. Your house disappears completely. Your city, even a major metropolitan area like New York or Los Angeles, shrinks to a microscopic bump on the surface of the sand grain. You would need a powerful microscope just to detect it, but we are just getting started with this exercise. If Earth shrinks to sand grain size, our moon becomes a small pebble floating 20 feet away. The sun transforms into a beach ball positioned half a mile down the road. Jupiter grows to the size of a large marble rolling around 3 miles from your position. These distances already stretch beyond comfortable human experience. Half a mile feels manageable. 3 miles requires a decent walk, but the nearest star, Proxima Centauri, now sits 125,000 miles away. You could not drive there. You could not fly there in a commercial airliner. You would need a rocket ship just to reach our nearest stellar neighbour in this sand grain universe. This scale model reveals something shocking about space. The distances between objects in our solar system, which already seem impossibly large, represent practically nothing compared to interstellar space. We live crammed together in a tiny pocket of warmth and matter, surrounded by an emptiness so complete it defies comprehension. Our entire solar system on this scale fits comfortably within a circle roughly 10 miles across, but the next solar system sits 125,000 miles away. The emptiness between star systems stretches 12,000 times further than the entire width of our local planetary family. However, even these staggering distances pale compared to the full extent of our galaxy. If we maintain this sand grain scale, Our galactic home stretches 11 billion miles from edge to edge. 11 billion miles. Light would require 16 hours to cross that distance, even at its incredible speed of 670 million miles per hour. But this comparison still fails to capture the true strangeness of galactic scale, because we have only dealt with distance so far. Right now, as you sit reading these words, you are moving faster than any human has ever travelled. You are not simply spinning with Earth's rotation, which carries you eastward at roughly 1,000 miles per hour. You are not just orbiting around the Sun with our planet, which adds another 67,000 miles per hour to your velocity. You are participating in something far more spectacular and violent than either of those familiar motions. Our entire solar system rockets through space at 560,000 miles per hour. This speed defies human experience. The fastest jet fighters reach roughly 1,500 miles per hour. The supersonic Concorde passenger jet managed about 1,350 miles per hour. Space rockets achieve maybe 25,000 miles per hour when escaping Earth's gravity. But we, sitting perfectly still in our chairs, travel through the cosmos at speeds that make all human transportation look like leisurely strolls. What drives this incredible velocity? We orbit something. Our Sun, along with its family of planets, moons, asteroids, and comets, wheels around a gravitational center located roughly 26,000 light-years away from us. We circle this center like a stone whirling on the end of a string, but the string stretches across distances that light requires 26,000 years to traverse. This orbital motion carries our solar system on a path so enormous that completing one revolution takes 250 million years. 250 million years. When our solar system last occupied this same position in space, dinosaurs had not yet evolved. The supercontinent Pangaea was just beginning to form. Life on Earth consisted primarily of simple marine creatures. We have completed less than 20 trips around this cosmic center since our planet formed. Earth has existed for roughly 4.5 billion years, but we have only managed 18 full orbits of our galaxy during that entire time span. Our planet is 18 galactic years old. This puts our existence in perspective. All of human history, from the first stone tools to space exploration, has occurred during less than 1% of a single galactic orbit. Rome rose and fell. Civilizations emerged and vanished. Entire species evolved and went extinct, all while we moved through just a tiny slice of our cosmic neighborhood. But what exactly sits at the center of this vast orbital dance? What massive object possesses enough gravitational pull to drag our solar system and hundreds of billions of other stars around in this slow, stately procession? The answer involves something so extreme that it warps space itself. For most of human history, we believed we occupied the center of creation. Earth sat motionless while the sun, moon, planets, and stars wheeled around us in perfect circles. This made sense. We could feel no motion beneath our feet. We observed celestial objects rising and setting like clockwork. Obviously, we reasoned, everything else must be moving while we remained stationary at the cosmic center. This comfortable assumption lasted until astronomers developed better instruments and started measuring things more carefully. First, they discovered that Earth orbits the Sun rather than the reverse. This demotion stung, but at least our Sun might still occupy the center of something larger. Then in 1917, astronomer Harlow Shapley made a discovery that shattered even this modest hope. Shapley studied globular clusters, dense balls of ancient stars that hover around our galaxy like fireflies around a campfire. He measured their distances and mapped their positions in space. What he found shocked the scientific community. These stellar clusters did not center themselves around our solar system. They did not even center themselves around our local region of space. Instead, they clustered around a point roughly 30,000 light-years away from us in the direction of the constellation Sagittarius. Our solar system sat far out toward the edge of this vast collection, like a cabin in the suburbs of a major metropolitan area. We were not at the center. We were not even close to the center. We inhabited the galactic equivalent of a rural outpost. This discovery revealed that we live inside something much larger than anyone had imagined. Shapley calculated that our galaxy stretches roughly 100,000 light-years from edge to edge. Our solar system sits about 26,000 light-years from the galactic center, placing us closer to the outer edge than to the middle. If our galaxy were a pizza, we would live somewhere out near the crust, definitely not enjoying a prime location near the center where all the good toppings concentrate. This positioning actually benefits us tremendously, though we did not realize it at the time. The galactic center turns out to be a violent, hostile environment filled with intense radiation, gravitational chaos, and exotic phenomena that would sterilize any nearby planets. Our suburban location provides a quiet, stable environment where complex chemistry can evolve over billions of years. But Shapley's revelation raised a new question. If we orbit something 30,000 light-years away, what could possibly be massive enough to gravitationally bind hundreds of billions of stars into this enormous spinning structure? The answer would not come for decades, and when it did, it would prove stranger than anyone expected. Measuring the width of our galaxy presented astronomers with an impossible challenge. How do you measure something when you are trapped inside it? How do you determine the size of a forest when you are standing between the trees? How do you map the borders of a city when you cannot leave the city limits? Astronomers faced exactly this problem when they tried to figure out how big our galactic home actually was. Harlow Shapley solved this puzzle using a clever trick. He could not step outside our galaxy to measure it directly. So instead, he mapped the locations of globular clusters, those dense balls of ancient stars that orbit our galactic center like distant streetlights. Shapley knew that these globular clusters surrounded our galaxy in a roughly spherical halo. If he could measure the distances to enough clusters and plot their positions in three-dimensional space, he could outline the invisible boundaries of our galactic home. The clusters would act like survey markers, defining the edges of something too large to see directly. This required solving another seemingly impossible problem: measuring distances to objects tens of thousands of light-years away. Shapley accomplished this by studying Cepheid variable stars, special stars that pulse brighter and dimmer in a predictable pattern. Amazingly, the rate at which these stars pulse directly relates to their actual brightness. A Cepheid that pulses slowly shines intrinsically brighter than one that pulses quickly. This relationship gave Shapley a cosmic ruler. When he observed a Cepheid variable star, he could time its pulsing pattern to determine how bright it actually was. Then he could compare that true brightness to how bright it appeared from Earth. The difference between actual brightness and observed brightness revealed the distance, because more distant objects always appeared dimmer than nearby ones. Using this technique, Shapley measured distances to dozens of globular clusters scattered around the sky. When he plotted their positions, a pattern emerged. The clusters outlined a vast spherical region roughly 100,000 light-years across. Our solar system sat nowhere near the center of this sphere. Instead, we occupied a position about 2/3 of the way toward the edge. This measurement shocked everyone, including Shapley himself. 100,000 light-years exceeded every previous estimate of galactic size by enormous margins. Most astronomers had assumed our galaxy might stretch a few thousand light-years across, comparable to the distances between nearby stars. Instead, Shapley revealed that we inhabit something truly cosmic in scale. 100,000 light-years means that light traveling at 670 million miles per hour requires 100,000 years to cross from one side of our galaxy to the other. His measurement has held up remarkably well. Modern techniques have refined his estimate slightly, but Shapley got the basic scale exactly right, using instruments that seem primitive by today's standards. However, Shapley's globular clusters mapped only the visible boundaries of our galaxy. Something invisible surrounds us. We cannot see it. We cannot touch it. We cannot detect it with any normal instrument. Yet this mysterious substance outweighs everything visible in our galaxy by a ratio of roughly 20-1. Stars, planets, gas clouds, dust particles, and all the normal matter we can observe account for only about 5% of our galactic home. The other 95% consists of something we call dark matter. How do we know invisible matter exists if we cannot detect it directly? The same way we know wind exists when we cannot see air. We observe its effects on other things. Stars in the outer regions of our galaxy orbit the galactic center too quickly. They move so fast that they should fly apart and scatter into intergalactic space, like mud flying off a spinning tire. The gravitational pull of all the visible matter in our galaxy cannot provide enough force to hold these speeding stars in stable orbits. Something else must be out there, something massive enough to generate the additional gravitational pull required to keep our galaxy intact. This invisible mass forms a roughly spherical halo around our galaxy, extending far beyond the visible star-filled disk. Recent measurements suggest this dark matter halo stretches nearly 2 million light-years across. 2 million light-years. This means the true boundary of our galactic home extends 20 times further than the visible stars. Most of our galaxy consists of empty space, filled with invisible particles we do not understand. Think of it this way. If our visible galaxy were a flashlight beam in a dark room, the dark matter halo would be the entire room surrounding that small cone of light. We live inside the beam, surrounded by vast volumes of invisible mass that we can only detect through its gravitational influence. This dark matter does not behave like normal matter. It does not emit light. It does not absorb light. It does not interact with electromagnetic radiation at all. Dark matter particles can pass right through normal matter as if it were not even there. Billions of dark matter particles flow through your body every second without any interaction whatsoever. Scientists estimate that roughly 600 billion to 3 trillion times the mass of our Sun worth of dark matter fills the halo around our galaxy. This invisible mass shapes the structure and evolution of our galactic home in ways we are only beginning to understand. The existence of dark matter raises profound questions about the nature of reality. Most of the universe consists of something we cannot see, touch, or directly detect. We inhabit a cosmos where the familiar matter that makes up stars, planets, and ourselves represents a tiny minority component. But even this invisible halo has boundaries, and beyond those boundaries lies something even more mind-bending. In 1977, humanity launched 2 robotic explorers toward the outer planets. Voyager 1 and Voyager 2 represent the fastest objects humans have ever sent into deep space. They race away from our solar system at roughly 38,000 miles per hour, fast enough to cross the United States in less than 5 minutes. These spacecraft have travelled further from Earth than any human creation, carrying messages to possible alien civilizations and returning stunning images of distant worlds. But their incredible speed, achieved through careful gravitational assists from multiple planets, still proves pathetically inadequate for galactic travel. At 38,000 miles per hour, Voyager 1 would require 173,000 years just to reach our nearest stellar neighbour if it were actually headed in that direction. 173,000 years. This exceeds the entire span of human civilization by a factor of 10. Agriculture, writing, cities, empires, industry, and space travel all developed during a time period much shorter than the journey to our closest stellar neighbor. But reaching the next star over represents barely the first step in galactic exploration. To cross the full width of our galaxy would require Voyager 1.7 billion years of constant travel. 1.7 billion years. This time span dwarfs not just human history, but the entire history of complex life on Earth. When Voyager began such a hypothetical journey, the most advanced life forms on our planet would have been simple bacteria and algae. Multicellular organisms had not yet evolved. Animals did not exist. Plants did not exist. The Earth's atmosphere contained almost no oxygen. During the billion-plus years required for Voyager to cross our galaxy, life evolved from single cells to the complexity of human civilization. This puts galactic distances in biological perspective. Evolution from microbes to mammals and minds takes less time than crossing our cosmic neighborhood at the fastest speed our technology can achieve. This calculation assumes Voyager could somehow maintain its speed indefinitely without running out of fuel, breaking down, or colliding with anything. In reality, both Voyager spacecraft will go silent within the next decade as their nuclear power sources decay. They will continue coasting through space as dead hunks of metal and plastic, but they will never report back about what lies in the darkness between stars. The vast emptiness between stellar systems creates an almost perfect vacuum. Voyager encounters less than 1 atom per cubic centimetre in the space between stars. This represents a vacuum more complete than anything we can create in laboratories on Earth. The spacecraft travels through regions so empty that it might not encounter another solid object for millions of years. This emptiness defines the structure of our galaxy. Stars cluster together in a flat disk, but enormous spaces separate each point of light from its neighbours. However, our galaxy contains much more than just individual stars scattered through empty space. Our galaxy contains more stars than there are grains of sand on all the beaches of Earth. 400 billion stars shine within the boundaries of our cosmic neighbourhood. 400 billion. This number exceeds human comprehension. If you counted one star every second, 24 hours a day, it would take you over 12,000 years to count them all. If every person currently alive on Earth took responsibility for counting a different group of stars, each person would need to count roughly 50 stars to complete the census. These stars come in an astounding variety of sizes, colours and ages. Some shine blue-white and burn through their nuclear fuel in just a few million years. Others glow red and sip their fuel so slowly they will continue shining for hundreds of billions of years, long after our sun dies. Some stars contain barely enough mass to sustain nuclear fusion, while others pack dozens of times more matter than our sun into incredibly dense, incredibly hot stellar cores. The diversity extends beyond simple size and temperature differences. Some stars exist in pairs, orbiting each other in elegant gravitational dances. Others cluster together in groups of dozens or hundreds, forming stellar cities where intense radiation and gravitational interactions create exotic phenomena. Some stars pulse with regular rhythms, acting like cosmic lighthouses sweeping beams across space. Among these 400 billion stars, at least 100 billion planets orbit in the habitable zones where liquid water could exist. 100 billion potentially habitable worlds scattered throughout our galactic home. Some of these planets might harbour life. Some might host civilizations. Some might contain intelligence advanced enough to contemplate the same questions we are exploring right now. The oldest stars in our galaxy formed over 13 billion years ago when the universe itself was young. These ancient suns have witnessed the entire history of cosmic evolution, from a time when heavy elements barely existed to the current epoch of rocky planets and complex chemistry. Some planetary systems around these old stars could have supported life for billions of years longer than Earth has existed. This vast stellar population does not distribute itself randomly throughout our galaxy. The stars organize themselves into a flattened disk roughly 1,000 light-years thick and 100,000 light-years across. Our solar system sits embedded within this disk about 26,000 light-years from the galactic center. From our position within the disk, we see the concentrated glow of billions of distant stars when we look toward the galactic center. This creates the bright band of the Milky Way that arches across our night sky. We are looking edge-on through the flat plane of our galaxy, seeing the combined light of countless suns too distant to resolve individually. But these 400 billion stars represent just the beginning of our galactic inventory. Our galaxy spins like a vast cosmic pinwheel, but its rotation follows rules unlike anything we experience on Earth. When a record spins on a turntable, all points on the record complete one revolution in the same amount of time. The center and the edge rotate together, maintaining their relative positions. But our galaxy behaves differently. Stars closer to the galactic center orbit much faster than stars farther out, like runners on a track where the inside lanes move at higher speeds than the outside lanes. Our solar system, positioned roughly 26,000 light-years from the galactic center, requires 250 million years to complete one orbit. 250 million years. Astronomers call this time span a cosmic year, and it provides a useful measure for galactic timescales. Since Earth formed 4.5 billion years ago, our planet has completed only 18 trips around the galaxy, 18 cosmic years. All of Earth's history, from the formation of the first rocks to the present moment, spans less than 20 galactic rotations. Consider what this means for the history of life. When Earth completed its previous orbit around the galaxy 250 million years ago, the supercontinent Pangaea was just beginning to break apart. Dinosaurs had not yet evolved. The most advanced life forms were primitive reptiles and amphibians. Mammals did not exist. Flowers did not exist. Grass did not exist. The entire age of dinosaurs, from their first appearance to their extinction 65 million years ago, lasted about 1/4 of a galactic year. Human civilization has existed for less than 1/10,000th of a cosmic year. If our galaxy's history were compressed into a single Earth year, human civilization would represent the last few seconds before midnight on December 31st. This slow rotation creates interesting consequences for stellar neighborhoods. Stars that currently sit near each other in space will drift apart over cosmic time. The patterns of constellations that seem permanent from human perspectives will completely rearrange themselves within a few million years. Our Sun's orbital path carries us up and down through the galactic disk as we circle the center. We spend about 33 million years above the disk's central plane, then dive down to spend 33 million years below it, creating a gentle bobbing motion that takes roughly 66 million years to complete one cycle. Some scientists suggest this vertical oscillation might correlate with mass extinction events on Earth. When our solar system passes through the disk's central plane, we encounter denser concentrations of gas, dust, and debris that could disrupt the outer reaches of our solar system and send comets tumbling toward the inner planets. Stars in different parts of our galaxy orbit at different speeds, creating a complex pattern of stellar motion that astronomers call differential rotation. At the exact center of our galaxy lurks something so massive and dense that it warps space and time. Sagittarius A star, the supermassive black hole at our galactic core, contains the mass of 4 million suns compressed into a region smaller than our solar system. 4 million suns. This gravitational monster exerts such powerful attractive force that it holds our entire galaxy together, binding 400 billion stars into a single rotating structure. This vast stellar population does not distribute itself randomly throughout our galaxy. The stars organize themselves into a flattened disk, roughly 1,000 light-years thick and 100,000 light-years across. Our solar system sits embedded within this disk, about 26,000 light-years from the galactic center. From our position within the disk, we see the concentrated glow of billions of distant stars when we look toward the galactic center. This creates the bright band of the Milky Way that arches across our night sky. We are looking edge-on through the flat plane of our galaxy, seeing the combined light of countless suns too distant to resolve individually. But these 400 billion stars represent just the beginning of our galactic inventory. Our galaxy spins like a vast cosmic pinwheel, but its rotation follows rules unlike anything we experience on Earth. When a record spins on a turntable, all points on the record complete one revolution in the same amount of time. The center and the edge rotate together, maintaining their relative positions. But our galaxy behaves differently. Stars closer to the galactic center orbit much faster than stars farther out, like runners on a track where the inside lanes move at higher speeds than the outside lanes. Our solar system, positioned roughly 26,000 light-years from the galactic center, requires 250 million years to complete one orbit. 250 million years. Astronomers call this time span a cosmic year, and it provides a useful measure for galactic timescales. Since Earth formed 4.5 billion years ago, our planet has completed only 18 trips around the galaxy, 18 cosmic years. All of Earth's history, from the formation of the first rocks to the present moment, spans less than 20 galactic rotations. Consider what this means for the history of life. When Earth completed its previous orbit around the galaxy 250 million years ago, the supercontinent Pangaea was just beginning to break apart. Dinosaurs had not yet evolved. The most advanced life forms were primitive reptiles and amphibians. Mammals did not exist. Flowers did not exist. Grass did not exist. The entire age of dinosaurs, from their first appearance to their extinction 65 million years ago, lasted about 1/4 of a galactic year. Human civilization has existed for less than 1/10,000th of a cosmic year. If our galaxy's history were compressed into a single Earth year, human civilization would represent the last few seconds before midnight on December 31st. This slow rotation creates interesting consequences for stellar neighborhoods. Stars that currently sit near each other in space will drift apart over cosmic time. The patterns of constellations that seem permanent from human perspectives will completely rearrange themselves within a few million years. Our Sun's orbital path carries us up and down through the galactic disk as we circle the center. We spend about 33 million years above the disk's central plane, then dive down to spend 33 million years below it, creating a gentle bobbing motion that takes roughly 66 million years to complete one cycle. Some scientists suggest this vertical oscillation might correlate with mass extinction events on Earth. When our solar system passes through the disk's central plane, we encounter denser concentrations of gas, dust, and debris that could disrupt the outer reaches of our solar system and send comets tumbling toward the inner planets. Stars in different parts of our galaxy orbit at different speeds, creating a complex pattern of stellar motion that astronomers call differential rotation. At the exact center of our galaxy lurks something so massive and dense that it warps space and time. Sagittarius A star, the supermassive black hole at our galactic core, contains the mass of 4 million suns compressed into a region smaller than our solar system. 4 million suns. This gravitational monster exerts such powerful attractive force that it holds our entire galaxy together, binding 400 billion stars into a single rotating structure. This video script is a comprehensive journey through our galaxy, the Milky Way, and our place within the broader cosmos. A black hole this massive creates effects that defy normal experience. Near its event horizon, the boundary beyond which nothing can escape, space itself gets stretched and twisted into impossible shapes. Time runs slower than it does here on Earth. Clocks would tick more slowly near this black hole than they do in your living room. We cannot see the black hole directly because it traps light along with everything else that ventures too close. But we can observe its effects on nearby objects. Stars that orbit close to Sagittarius A star reach speeds of over 3,000 miles per second as they whip around the invisible gravitational anchor. 3,000 miles per second. These stars complete orbital periods measured in years, not centuries or millennia. The black hole occasionally feeds when gas clouds, or even entire stars, wander too close to its gravitational grasp. As material spirals inward toward the event horizon, friction heats it to temperatures of millions of degrees. This superheated material glows brilliantly in X-rays and radio waves, before disappearing forever beyond the point of no return. Recent observations have revealed that Sagittarius A star spins at nearly the maximum rate possible for any black hole. It rotates so fast that it drags space itself along with its rotation, creating a phenomenon called frame dragging that was predicted by Einstein's theory of general relativity. This central black hole likely formed early in our galaxy's history, growing from a smaller seed by consuming gas, dust and stars over billions of years. As it grew larger, its gravitational influence expanded, allowing it to capture and organize the matter that would eventually become our spiral galaxy. The region immediately surrounding our galactic center resembles a cosmic war zone. Intense radiation, strong magnetic fields, and gravitational chaos create conditions hostile to planet formation or biological life. Dense concentrations of massive stars live fast and die young, exploding as supernovas that add even more energy to an already violent environment. Despite sitting 26,000 light-years away from this mayhem, we still feel the black hole's gravitational influence. It provides the central anchor point around which our entire solar system orbits, along with all the other stars in our galactic neighborhood. But Sagittarius A star represents just one component of a much larger and more complex galactic structure. We face a problem that no other astronomers in the universe share. We live inside the thing we are trying to study. Every other galaxy in the universe can be observed from the outside, photographed in its entirety, and mapped from a comfortable external vantage point. We alone must piece together the structure of our cosmic home from clues gathered while trapped within its boundaries. Imagine trying to map the layout of a vast city while locked inside a basement apartment with no windows. You could send observers to different street corners to report what they see, but you could never. Step back to view the whole metropolitan area from above. This describes our situation exactly. When we look toward the center of our galaxy, we peer through the flat disk that contains most of our galactic home's stars and dust. Thick clouds of interstellar material block our view like fog, absorbing visible light before it can reach our telescopes. We can see only a few thousand light-years through this cosmic smog before everything disappears into darkness. Radio waves and infrared light penetrate this galactic fog better than visible light, allowing us to probe deeper into our galaxy's structure. But even these longer wavelengths cannot give us the clear, comprehensive view that astronomers studying external galaxies take for granted. Our edge-on perspective creates another problem. When we look along the plane of our galactic disk, we see the combined glow of billions of distant stars blending together into the bright band we call the Milky Way. Individual stars become impossible to distinguish at large distances. We lose all sense of three-dimensional structure and depth. This viewing challenge has led to some spectacular discoveries, though. Because we sit inside our galaxy, we can study individual stars much more closely than astronomers observing external galaxies can manage. We can measure the properties of stellar neighborhoods, map the chemical composition of gas clouds, and detect planets around nearby stars with precision that would be impossible from outside our galactic boundaries. Recent space missions have begun to overcome some of these observational limitations. The Gaia spacecraft has measured precise positions and motions for over 1 billion stars, creating the most detailed three-dimensional map of our galactic neighborhood ever attempted. These measurements reveal patterns of stellar motion that help us understand our galaxy's overall structure and history. Still, we will never enjoy the luxury of stepping outside our galaxy to photograph it from a distance. We must remain forever trapped within our cosmic home, like creatures living their entire lives inside a vast mansion, able to explore individual rooms but never able to appreciate the building's complete architecture. This limitation makes our next discovery all the more remarkable, because it involves features we cannot see directly but can only infer from subtle gravitational clues. The beautiful spiral arms that define our galaxy's appearance exist as phantom structures, more like cosmic traffic jams than solid objects. Most people imagine galactic spiral arms as fixed features, like the arms of a giant pinwheel rotating through space. But this picture proves completely wrong. The spiral arms we observe contain no permanent matter. Instead, they represent zones where stars and gas temporarily crowd together before dispersing back into the general galactic disk. Think of rush hour traffic on a busy highway. Cars bunch up around construction sites or accidents, creating dense concentrations that move much slower than individual vehicles. From an airplane, these traffic jams look like solid structures crawling along the roadway, but no individual car remains trapped in the jam permanently. Cars constantly enter the crowded zone from behind and exit ahead, while the jam itself maintains its shape and location. Our galaxy's spiral arms work exactly the same way. Individual stars orbit the galactic center at their own speeds, occasionally passing through spiral arms like cars passing through traffic jams. The arms themselves represent waves of compression that sweep around our galaxy, creating temporary concentrations of stars, gas, and dust. These compression waves trigger intense episodes of star formation as they squeeze gas clouds to higher densities. New stars ignite in brilliant blue clusters, illuminating the spiral arms and making them visible across vast distances. The brightest, most massive stars burn out quickly, dying as spectacular supernovas before they can drift away from their birthplace. This creates the illusion that spiral arms contain permanent populations of young, bright stars. Our solar system currently sits between two major spiral arms in a smaller spur called the Orion Arm. We completed our last passage through a major spiral arm roughly 50 million years ago, and will not encounter another for approximately 10 million more years. During our travels through spiral arms, our solar system experiences higher concentrations of gas, dust, and radiation that might influence Earth's climate and biology. The spiral structure itself rotates around our galaxy much slower than individual stars orbit. This creates the differential motion that allows stars to pass in and out of spiral arms over cosmic time. If spiral arms rotated at the same speed as stars, they would quickly wind up into tight spirals and disappear within a few 100 million years. Scientists still debate exactly what creates and maintains our galaxy's spiral structure. Gravitational interactions with smaller companion galaxies might pump energy into the disk, sustaining the compression waves over billions of years. Alternatively, the central bar-shaped region of our galaxy might drive spiral patterns through complex gravitational dynamics. Recent observations have revealed that our spiral arms show remarkable complexity, with branches, spurs, and gaps that change over time scales of tens of millions of years. But these spiral arms, impressive as they appear, represent just the most visible component of something far more vast and mysterious. Our galaxy does not travel alone through the cosmic dark. When you zoom out far enough to see beyond our galactic boundaries, a surprising sight emerges. Small companion galaxies orbit around us like moths circling a campfire. These cosmic satellites, though dwarfed by our 400 billion star collection, contain millions or even billions of stars of their own. They dance attendance on our massive galactic home, bound by gravitational threads stretching across hundreds of thousands of light years. The two most famous companions shine prominently in southern hemisphere skies. The large and small Magellanic Clouds appear as fuzzy patches of light, looking like detached pieces of our own Milky Way. Early ocean navigators used these celestial landmarks for navigation, never suspecting they were actually gazing at entire galaxies in their own right. The large Magellanic Cloud contains roughly 10 billion stars and sits 160,000 light-years away from us. The small Magellanic Cloud, with about 3 billion stars, lies slightly further out at 200,000 light-years. These distances place both galaxies well beyond the edge of our visible stellar disk, but still within our extended dark matter halo. These companion galaxies do not orbit peacefully, though. Our massive gravitational influence distorts their shapes, stretching and warping their stellar populations like taffy being pulled. Long streams of gas and stars get torn away from both Magellanic Clouds, creating vast ribbons of matter that trail behind them as they circle our galactic center. But the Magellanic Clouds represent just the largest members of a much more extensive galactic family. Over 30 smaller satellite galaxies populate our local neighborhood, most containing only a few million stars each. These tiny galaxies bear exotic names like Draco, Sculptor, and Fornax, named after the constellations in which they appear from our perspective. Many of these satellite galaxies are so faint that we only discovered them recently, using sensitive electronic detectors to pick out their dim glow against the background stars. Some contain so little normal matter that they consist almost entirely of dark matter, making them nearly impossible to detect, despite containing the mass of millions of suns. Our gravitational influence on these companions proves devastating over cosmic time. As they orbit through our extended halo, tidal forces gradually strip away their outer stars, feeding our galaxy's growth. We are slowly cannibalizing our smaller neighbors, growing larger at their expense in a process that has continued for billions of years. This galactic cannibalism reveals something profound about how large galaxies like ours form and evolve. The galaxy you can see represents only the bright core of something vastly larger and almost entirely invisible. Recent measurements reveal that our dark matter halo extends nearly 2 million light-years from our galactic center. 2 million light-years. This means the true boundary of our galactic home stretches 20 times further than the visible edge of our stellar disk. Most of our galaxy consists of empty space filled with invisible matter that we can detect only through its gravitational effects. Imagine our visible galaxy as a cherry pit sitting in the center of a basketball. The cherry pit represents the 100,000 light-year disk containing all our familiar stars, gas, and dust. The basketball represents the true extent of our galactic domain, filled with dark matter particles that interact with nothing except gravity. This invisible halo contains at least 10 times more mass than all the visible matter in our galaxy combined. 600 billion to 3 trillion solar masses worth of dark matter surrounds us in a roughly spherical cloud that dwarfs everything we can actually observe. We live inside this vast invisible structure like deep-sea creatures, inhabiting the illuminated zone of an ocean that extends far beyond their experience. The dark matter halo shapes the behavior of everything within its boundaries. Satellite galaxies orbit through this invisible medium, experiencing gravitational forces from matter they cannot see or touch. The orbital paths of our companion galaxies trace out the true gravitational architecture of our cosmic home, revealing the presence of dark matter through their motions. Recent computer simulations suggest our dark matter halo contains thousands of smaller subhalos, dense concentrations of invisible matter that move through the larger structure like schools of fish swimming through the ocean. Some of these subhalos might be massive enough to capture normal matter and form small satellite galaxies. Others remain forever dark, consisting entirely of particles that never interact with photons. This extended dark matter envelope determines our galaxy's relationship with the broader universe. The halo's gravitational influence reaches out to capture gas falling in from intergalactic space, providing the raw material for continued star formation. It also shields us from some of the violence of the cosmic environment, deflecting high-speed particles and smaller objects that might otherwise disrupt our galaxy's delicate structure. The boundary between our dark matter halo and intergalactic space remains poorly defined. The halo's density gradually decreases with distance from our galactic center, eventually becoming so thin that it merges imperceptibly with the general dark matter background that fills all of space. But even this enormous invisible structure represents just one component of an even grander cosmic architecture. Our galaxy is not the stable, perfectly balanced disk that most people imagine. Instead, our cosmic home wobbles and flexes like a spinning coin slowly losing momentum. The outer edges of our galactic disk warp up and down, creating ripples that propagate inward toward the center like waves on a disturbed pond. This warping motion represents one of the most dynamic and surprising aspects of our galactic structure. Recent observations using variable stars of different ages have revealed that our galaxy's warp precesses or rotates in a backward direction at roughly 1,200ths of a degree every million years. This means the warp pattern itself slowly rotates around our galactic center in the opposite direction from our star's orbital motion. What causes this strange wobbling motion? The culprit appears to be our dark matter halo. Computer models suggest that our invisible halo has a slightly flattened shape, like a football rather than a perfect sphere. As our stellar disk rotates within this oblate dark matter distribution, gravitational torques create the wobbling motion that we observe. Think of a coin spinning on a table. As friction slows the coin's rotation, it begins to wobble more and more dramatically until it finally falls flat. Our galaxy experiences similar dynamics, but instead of friction, the misalignment between our rotating disk and the principal axis of our dark matter halo creates the torques that drive the wobbling motion. This galactic wobble affects everything within our cosmic neighborhood. Stars in the outer regions of our disk experience vertical accelerations as they ride the warping waves. Gas clouds get compressed and stretched as the disk flexes around them. Even our solar system, though relatively close to the galactic center, participates in this slow cosmic dance. The wobbling motion also provides crucial information about the distribution of dark matter around our galaxy. By measuring how the warp precesses, astronomers can infer the shape and orientation of the invisible halo that dominates our galactic mass. This gives us one of the few direct ways to probe the properties of dark matter on galactic scales. Satellite galaxies contribute additional complications to our galactic wobble. The large and small Magellanic Clouds, along with our smaller companion galaxies, exert their own gravitational influences on our disk structure. Their orbital motions create additional torques that modify the precession rate and pattern of our galactic warp. This discovery reveals that our galaxy exists in a constant state of dynamic evolution, continuously responding to gravitational influences from both visible and invisible matter. However, our wobbling disk faces an even more dramatic future transformation. 4.5 billion years from now, our night sky will be transformed by one of the most spectacular events in cosmic history. The Andromeda galaxy, our nearest large galactic neighbour, races toward us at roughly 250,000 miles per hour. This colossal collection of 1 trillion stars will collide with our galaxy in what astronomers call the most predictable cosmic catastrophe. The merger will reshape both galaxies beyond recognition, creating a new cosmic structure from the debris of our current homes. Right now, Andromeda appears as a faint smudge of light in our autumn skies, barely visible to the naked eye, despite containing more stars than our entire galaxy. But this seemingly delicate spiral sits only 2.5 million light-years away, making it the closest large galaxy to our own. In cosmic terms, we practically share the same neighbourhood. As Andromeda approaches, its gravitational influence will begin disrupting our galaxy's structure long before the actual collision occurs. Our outer spiral arms will stretch and distort. Streams of stars will get pulled away from both galaxies, creating vast bridges of matter spanning the gap between the two cosmic titans. The collision itself will unfold over billions of years, a slow-motion catastrophe that spans timescales unimaginable to human experience. Despite containing over 1 trillion stars between them, individual stellar collisions will remain extremely rare due to the vast distances separating each point of light. Instead, the collision will resemble 2 clouds of fireflies passing through each other, with gravitational interactions scrambling the orbital paths of most stars. Our Sun will likely survive this cosmic merger, though its fate remains uncertain. Computer simulations suggest our solar system might get flung into the outer regions of the merged galaxy, or possibly even ejected entirely into intergalactic space. Earth may find itself orbiting a star that wanders forever between galaxies, with no galactic home to call its own. The supermassive black holes at the centers of both galaxies will spiral inward toward each other during the merger, eventually combining into a single gravitational monster containing the mass of over 5 million suns. This black hole merger will release more energy and gravitational waves than our Sun will emit in light over its entire 10 billion year lifetime. The resulting merged galaxy, which astronomers have nicknamed Milky, will bear no resemblance to either of its parent structures. Instead of 2 elegant spiral galaxies, the collision will produce a single elliptical galaxy, a roughly football-shaped collection of stars with no organized structure or spiral arms. But this collision represents just one example of the violent cosmic environment that surrounds us. Our entire local group of galaxies, including both the Milky Way and Andromeda, rushes through space towards something massive and mysterious at 600 miles every second. That represents our collective velocity toward a gravitational anomaly that astronomers call the Great Attractor. This invisible mass concentration lies roughly 150 million light-years away in the direction of the constellations Hydra and Centaurus. Hidden behind the dust and stars of our own galactic disk, the Great Attractor exerts gravitational pull on thousands of galaxies across hundreds of millions of light-years. Its influence reaches so far that it affects the motion of our entire cosmic neighborhood, dragging galaxy clusters and superclusters toward itself like debris caught in a cosmic whirlpool. What could possibly be massive enough to gravitationally dominate such enormous volumes of space? The Great Attractor contains the mass equivalent of tens of thousands of galaxies like our own, concentrated into a region roughly 500 million light-years across. This represents one of the largest structures in the known universe, a gravitational anchor point that shapes the motion of matter across vast cosmic distances. The mystery deepens because the Great Attractor sits partially hidden behind our own galaxy. When we look in that direction, the stars and dust of our galactic disk block our view of whatever lies beyond. Astronomers call this the zone of avoidance, a region where observations become extremely difficult due to obscuration by our own cosmic home. Using telescopes that can see through dust, astronomers have identified several massive galaxy clusters in the direction of the Great Attractor. The Norma cluster, the Centaurus cluster, and the Hydra cluster all contribute to the gravitational pull that affects our motion through space. But even adding up all these visible structures cannot account for the total attractive force that we observe. Something else must be out there. Additional mass, possibly in the form of dark matter concentrations or hidden galaxy clusters, contributes to the Great Attractor's gravitational influence. The complete inventory of matter responsible for our cosmic motion remains unknown, hidden behind the veil of our own galaxy's obscuring material. This discovery reveals that our galaxy does not move randomly through space. Instead, we follow gravitational currents established by the largest structures in the universe. We are passengers on a cosmic river, carried along by forces that operate on scales dwarfing even our massive galactic home. Recent observations have revealed an even larger structure beyond the Great Attractor. The Shapley supercluster, containing thousands of galaxies, may represent the ultimate destination of our cosmic journey. But the gravitational drama playing out in our cosmic neighborhood involves more than just these distant attractors. Our galaxy acts as a cosmic predator, slowly devouring smaller neighbors that venture too close. The Sagittarius dwarf elliptical galaxy provides a perfect example of this galactic cannibalism in action. This small collection of roughly 4 billion stars currently passes through our galaxy's disk, being shredded by our gravitational forces as it attempts to complete its orbit around our galactic center. Over the past few billion years, our gravity has stripped away most of the Sagittarius dwarf's original stellar population. Long streams of stars now trail behind the disrupted galaxy like ribbons, marking its orbital path through our galactic halo. These stellar streams wrap completely around our galaxy, creating rings of stars that move in lockstep with their parent galaxy's motion. The destruction happens slowly but inexorably. Each time the Sagittarius dwarf passes through our dense galactic disk, tidal forces tear away its outermost stars. The dwarf galaxy shrinks with each passage, losing mass and gradually dissolving into our larger stellar population. Computer simulations suggest that within the next few billion years, the Sagittarius dwarf will completely disappear, its stars fully integrated into our galactic structure. This process of galactic cannibalism has shaped our galaxy's growth throughout cosmic history. Many of the stars in our galactic halo likely originated in small satellite galaxies that our gravity captured and destroyed over the past 10 billion years. The smooth distribution of stars in our halo actually represents the blended remains of dozens or hundreds of smaller galaxies. The Large Magellanic Cloud faces a similar fate, though its destruction will unfold over a much longer time span. Recent measurements of its motion suggest that it may not be in a stable orbit around our galaxy. Instead, the Large Magellanic Cloud might be making its first close approach to our galactic neighborhood, having recently been captured by our extended gravitational influence. As the Large Magellanic Cloud spirals inward over the next several billion years, our gravity will gradually strip away its outer stars and gas. The galaxy's death throes will feed new episodes of star formation in our own disk, as its gas content gets incorporated into our spiral arms. Even our smallest satellite galaxies show signs of this ongoing destruction. Ultra-faint dwarf galaxies containing only a few thousand stars bear the scars of tidal disruption. Their elongated shapes and disturbed stellar distributions reveal the gravitational violence they have experienced during their passages through our galactic environment. This galactic predation represents a fundamental aspect of cosmic evolution. Large galaxies like ours grow primarily by consuming smaller neighbors rather than by accumulating matter directly from intergalactic space. The evidence for this cosmic cannibalism surrounds us, written in the motions and distributions of stars throughout our galactic home. For decades, astronomers debated whether our galaxy possessed one of the most common features found in spiral galaxies throughout the universe. Most spiral galaxies contain a central bar, an elongated concentration of stars that extends outward from the galactic nucleus like the handle of a cosmic dumbbell. These stellar bars play crucial roles in galactic evolution, channeling gas inward to feed star formation and helping to drive the spiral arm patterns that define galaxy structure. But discovering whether our own galaxy contains such a feature proved remarkably difficult. The problem arose from our position within the galactic disk. When you live inside a galaxy, detecting its large-scale structure becomes like trying to map the shape of a forest while standing among the trees. Dust clouds scattered throughout our galactic disk absorb visible light, creating a zone of obscuration that blocks our view of the galactic center and makes structural analysis nearly impossible. The breakthrough came in 2005 when the Spitzer Space Telescope used infrared light to peer through the dust and map the distribution of stars in our galaxy's central regions. Infrared radiation penetrates cosmic dust much better than visible light, allowing astronomers to see through the obscuring material that had hidden our galaxy's inner structure for so long. The infrared observations revealed a startling truth. Our galaxy does indeed contain a central bar stretching roughly 27,000 light-years from end to end. This massive stellar structure contains billions of stars arranged in an elongated pattern that rotates as a single rigid body around our galactic center. The discovery explained several puzzling observations about our galaxy's behavior. The central bar helps drive our spiral arm pattern by creating gravitational disturbances that compress gas clouds as they orbit around our galaxy. It also channels material inward toward our central supermassive black hole, providing the fuel for occasional feeding episodes. Our galactic bar rotates faster than our solar system orbits, completing one revolution every few 100 million years. This means that different parts of our galaxy periodically line up with the bar's gravitational influence, creating waves of star formation that propagate outward through our spiral arms. The bar's existence also affects our galaxy's long-term evolution. As it rotates, the bar slowly loses angular momentum to the surrounding disk, causing it to grow longer and more prominent over cosmic time. Computer simulations suggest that our bar formed relatively recently in galactic terms, probably within the last few billion years. This discovery revolutionized our understanding of our galaxy's architecture. Rather than a simple spiral galaxy with a circular central bulge, we inhabit a barred spiral galaxy with a complex internal structure that drives much of the dynamic behavior we observe in our cosmic neighborhood. The bar represents just one component of our galaxy's surprisingly complex and active interior structure. Across the vast expanse of our galaxy, approximately 3 new stars ignite every year, while 2 others reach the end of their stellar lives. This cosmic birth and death cycle has continued for over 10 billion years, gradually converting the primordial hydrogen and helium that filled our galaxy into the heavy elements that make rocky planets and biological life possible. Every atom in your body, except for hydrogen, was forged in the nuclear furnaces of massive stars that lived, died, and scattered their processed contents into space. Star formation does not occur randomly throughout our galactic disk. Instead, it concentrates in the spiral arms where compression waves squeeze gas clouds to higher densities. These stellar nurseries shine brilliantly with the light of newborn stars, creating the bright patterns that make spiral galaxies visible across billions of light-years of space. The most massive stars, containing 10 to 100 times more matter than our Sun, burn through their nuclear fuel in just a few million years before exploding as supernovas. These stellar explosions release more energy in seconds than our Sun will emit over its entire 10 billion year lifetime. The shock waves from supernovas compress nearby gas clouds, triggering new rounds of star formation in a self-perpetuating cycle. Lower mass stars like our Sun burn their fuel much more slowly, shining steadily for billions of years before gradually swelling into red giants and eventually shrinking to white. Dwarf remnants. These long-lived stars provide stable sources of energy that could potentially support biological evolution on orbiting planets over cosmic timescales. The chemical composition of new stars has changed dramatically over our galaxy's history. The first generation of stars formed from pure hydrogen and helium, the only elements that existed after the Big Bang. When these primordial stars died, they scattered heavier elements into space through stellar winds and supernova explosions. Each subsequent generation of stars incorporated these heavier elements, gradually enriching our galaxy with carbon, oxygen, silicon, iron, and all the other elements necessary for complex chemistry. Our Sun, formed roughly 4.6 billion years ago, represents at least a third-generation star built from material processed through multiple cycles of stellar birth and death. The current star formation rate in our galaxy has declined significantly from its peak roughly 10 billion years ago. During our galaxy's youth, new stars ignited at rates perhaps 10 times higher than today. This slowdown reflects the gradual depletion of the raw materials necessary for star formation as more and more gas gets locked up in long-lived stellar remnants. Computer models suggest that our galaxy will continue forming stars for many billions of years to come, but at steadily decreasing rates. Eventually, star formation will cease entirely when our galaxy exhausts its supply of gas and dust. This stellar recycling process operates on scales that encompass our entire galactic home. The boundary of our galaxy refuses to stay put. For decades, astronomers assumed that our galaxy's stellar disk ended at a well-defined edge, roughly 50,000 light-years from the galactic center. Beyond this point, they expected to find only empty space populated by the occasional globular cluster or stray star. But recent observations have shattered this comfortable assumption. In 2018, astronomers using data from the Gaia space mission discovered stars belonging to our galactic disk at distances of 84,000 to 103,000 light-years from the center. These distant stellar populations exist far beyond what was once considered the absolute limit of our galaxy's structure, extending the known boundaries of our cosmic home by tens of thousands of light-years. Even more surprisingly, follow-up studies have pushed the detection of disk stars out to distances approaching 130,000 light-years from our galactic center. This means our galaxy stretches significantly farther than the canonical 100,000 light-year diameter that astronomers have used for over a century. But the stellar disk represents only part of the story. Recent measurements of our galaxy's dark matter halo suggest it extends nearly 2 million light-years from our center, 20 times farther than the visible stellar populations. The true boundary of our galactic domain reaches almost halfway to the Andromeda galaxy, our nearest large galactic neighbor. This extended structure creates a puzzle for models of galaxy formation and evolution. How can our galaxy maintain organized stellar populations at such enormous distances from the central gravitational anchor? The orbital periods of stars in these outer regions exceed 1 billion years, meaning they have completed only a handful of orbits since our galaxy formed. The discovery of this extended structure also raises questions about where our galaxy ends and intergalactic space begins. If our dark matter halo stretches 2 million light-years, while Andromeda's halo extends a similar distance, the two halos may already be touching or overlapping. In this sense, the collision between our galaxies may have already begun, even though the stellar populations will not merge for another 4 billion years. Gravitational interactions with satellite galaxies may help explain some of these extended stellar populations. As our gravity tears apart smaller companion galaxies, their stars get scattered across vast volumes of space. Some of these disrupted stellar streams could account for the distant stars we now observe in our galaxy's outer regions. The continuing expansion of our galaxy's known boundaries reflects improvements in observational technology and data analysis techniques. Each new generation of telescopes and space missions reveals previously hidden components of our cosmic home, pushing the frontiers of the known ever farther outward. This pattern suggests that our galaxy's true extent may be even larger than current measurements indicate. Invisible magnetic highways spiral through our galaxy, channeling the flow of charged particles across distances that dwarf entire solar systems. These galactic magnetic fields, though thousands of times weaker than a refrigerator magnet, extend across the full 100,000 light-year expanse of our cosmic home. They thread through interstellar space like cosmic power lines, guiding the motion of electrically charged gas and influencing the birth and death of stars throughout our galactic neighborhood. The magnetic field lines follow the spiral pattern of our galaxy's structure, wrapping around our galactic center in great sweeping arcs that mirror the distribution of spiral arms. This alignment occurs because the rotation of our galaxy stretches and twists the magnetic field, much like wringing out a wet towel causes the water to align along spiral patterns in the fabric. These magnetic highways play crucial roles in galactic dynamics that remain invisible to our everyday experience. Charged particles, including cosmic rays accelerated by supernova explosions, follow the magnetic field lines as they travel through space. High-energy protons and electrons spiral along these invisible tracks, sometimes journeying thousands of light years before encountering obstacles that deflect their paths. The magnetic fields also influence star formation by providing support pressure that helps resist gravitational collapse in gas clouds. When magnetic field lines become tangled or compressed, they can either enhance or inhibit the formation of new stars, depending on the local conditions. This magnetic regulation helps explain why star formation occurs in some regions of our galaxy while leaving others relatively barren. Recent observations from space missions have begun mapping our galaxy's magnetic structure in unprecedented detail. The European Space Agency's Planck mission measured the polarization of light from interstellar dust grains, revealing how these particles align with local magnetic field directions. The resulting maps show a complex web of magnetic structures threading through our galactic disk. These magnetic fields originate from the motion of electrically conducting gas within our galaxy. As clouds of ionized hydrogen move through space, they generate electrical currents that produce magnetic fields. The rotation of our galaxy then amplifies and organizes these fields into the large-scale structure we observe today. The strength of our galaxy's magnetic field varies dramatically from region to region. Near the galactic center, intense stellar activity and the presence of our supermassive black hole create magnetic field strengths hundreds of times greater than the galactic average. In the quiet regions between spiral arms, the magnetic field becomes so weak that it barely influences the behavior of charged particles. Magnetic reconnection events, where field lines break and reconnect in different configurations, can release enormous amounts of energy across interstellar distances. These magnetic phenomena connect our galaxy's structure to the broader electromagnetic environment of the universe. Our galaxy exists as one ordinary member of an almost incomprehensibly vast cosmic population. Recent estimates suggest that the observable universe contains roughly 2 trillion galaxies, each a massive collection of stars, gas, and dark matter. 2 trillion. This number exceeds every previous estimate by enormous margins, revealing that the cosmos harbors far more galactic cities than anyone had imagined. Our Milky Way represents less than 1/1,000,000th of the total galactic population. Among this vast multitude, our galaxy ranks as decidedly average in most respects. With roughly 400 billion stars, we sit near the middle of the galactic mass distribution. Many galaxies contain fewer stars than we do, while others dwarf us completely. The largest elliptical galaxies harbour over 1 trillion stars, making our cosmic home look small by comparison. Our galaxy's structure also proves typical for spiral galaxies throughout the universe. Roughly 60% of all galaxies display spiral patterns similar to ours, with central bulges, flattened disks, and prominent spiral arms. We belong to one of the most common types of cosmic architecture, sharing structural similarities with billions of other spiral galaxies scattered across space. However, our galaxy does possess some unusual characteristics that set it apart from the cosmic norm. We live in a relatively quiet galactic neighborhood, far from the dense galaxy clusters where violent interactions and mergers occur frequently. Most galaxies in the universe inhabit much more crowded environments where gravitational encounters regularly disrupt galactic structure. Our galaxy also appears unusually isolated compared to most spiral galaxies. While we do have satellite galaxies and will eventually collide with Andromeda, many spiral galaxies exist in small groups or clusters where multiple large galaxies interact gravitationally. This relative isolation has allowed our spiral structure to remain stable for billions of years. The chemical composition of our galaxy falls within normal ranges for spiral galaxies of similar mass and age. The abundance of heavy elements in our stellar populations indicates that we have experienced typical rates of star formation and stellar recycling over cosmic time. Our Sun's metallicity, though slightly enriched compared to the galactic average, represents conditions found throughout many spiral galaxies. Perhaps most remarkably, our galaxy appears to be forming stars at rates consistent with other spiral galaxies in the current epoch. We belong to what astronomers call the green valley in galaxy color magnitude space, indicating that our star formation rate is gradually declining as we consume our available gas supply. This comparison reveals both our cosmic significance and insignificance. While our galaxy contains hundreds of billions of stars and spans hundreds of thousands of light years, it represents just one typical example of galactic architecture repeated across the observable universe. The existence of 2 trillion other galaxies raises profound questions about the likelihood of life and intelligence elsewhere in the cosmos. Our galaxy does not drift randomly through empty space, but instead travels along one strand of the largest structures in the known universe. The cosmic web represents the ultimate architectural framework of creation, a vast network of dark matter filaments that connect galaxy clusters across billions of light years. These invisible highways channel the flow of matter and energy on the largest scales imaginable, creating a spiderweb pattern that spans the entire observable universe. Our galaxy sits embedded within one of these cosmic web filaments, following a predetermined path established by the gravitational influence of dark matter concentrations that formed in the early universe. Like a train travelling along invisible tracks, we move through space guided by forces that operate on scales dwarfing even our massive galactic home. The cosmic web filaments form the backbone of cosmic structure, containing roughly 60% of all the matter in the universe. These filaments stretch between massive nodes where thousands of galaxies cluster together, creating a network that resembles the neural pathways in a vast cosmic brain. Empty voids containing almost no matter separate the filaments, like the spaces between brain cells. Computer. Simulations reveal that this web-like structure emerged naturally from tiny density fluctuations in the early universe. Over billions of years, gravity amplified these initial irregularities, causing matter to flow along preferential directions and creating the filament pattern we observe today. Galaxies formed at the intersections and along the lengths of these dark matter highways. Our local group of galaxies, including both the Milky Way and Andromeda, travels along a filament that extends toward the Virgo cluster, a massive collection of over 1,300 galaxies located roughly 54 million light-years away. This filament provides the gravitational framework that guides our motion through space and connects us to the broader cosmic structure. The filament we inhabit contains not only galaxies, but also vast reservoirs of hot ionized gas that fills the spaces between galactic neighbors. This intergalactic medium, heated to temperatures of millions of degrees, glows faintly in X-ray light and provides the raw material for continued galaxy formation and growth. Recent observations have begun to map the cosmic web directly by detecting this hot intergalactic gas and measuring the subtle gravitational lensing effects created by dark matter filaments. These studies confirm that our galaxy indeed travels along one of the universe's fundamental structural components. The cosmic web also influences our galaxy's evolution by regulating the flow of matter between galactic and intergalactic environments. Gas falling into our galaxy along the filament provides fuel for continued star formation, while galactic winds driven by supernovas and stellar radiation can escape along these same pathways. This cosmic context reveals that our galaxy's history and future remain intimately connected to the larger scales of cosmic organization. If we could somehow travel outside our galaxy and look back, we would witness one of the most beautiful sights in the universe. Our cosmic home would appear as an elegant spiral galaxy, its sweeping arms glowing with the light of billions of stars arranged in graceful curves that extend outward from a bright central bulge. Blue-white clusters of young massive stars would illuminate the spiral arms like Christmas lights strung along cosmic highways, while the warm yellow glow of older stars would fill the spaces between the arms with a more subdued radiance. The central bar-shaped structure would stretch across the galaxy's heart, its elongated concentration of ancient stars rotating slowly around the supermassive black hole at our galactic core. Dark lanes of dust would trace the spiral arms, creating intricate patterns of light and shadow that reveal the galaxy's internal structure and ongoing star formation activity. From this impossible external vantage point, we could observe the faint halo of globular clusters surrounding our galaxy like fireflies around a campfire. These ancient stellar cities would appear as tiny points of concentrated light, their orbits tracing out. The true three-dimensional shape of our galactic home. The extended dark matter halo would remain invisible, its presence detectable only through the gravitational effects on nearby objects. Our galaxy's disk would appear remarkably thin when viewed edge-on, resembling a cosmic pancake with a thickness less than 1/50th of its diameter. The galactic warp would be clearly visible from this perspective, showing how our outer regions bend up and down like a warped record album slowly spinning in space. The satellite galaxies would be clearly visible as smaller companions orbiting around our massive galactic home. Streams of stars torn from these disrupted neighbours would trace delicate arcs across the sky, recording the gravitational violence inflicted by our galaxy's tidal forces. The approaching Andromeda galaxy would loom in the distance, its own spiral structure clearly visible against the cosmic background. But we will never enjoy this external perspective. We remain forever trapped within our galactic home, like creatures living their entire lives inside a vast cathedral, able to examine individual architectural details, but never able to step outside and appreciate the building's complete design from a distance. This limitation defines the human condition on cosmic scales. We inhabit something far grander than ourselves, yet we can never fully comprehend its beauty or complexity because we cannot escape our position within it. We must piece together our galaxy's appearance from fragments and clues, like archaeologists reconstructing an ancient temple from scattered stones. Despite this limitation, we have succeeded in mapping our galactic home with remarkable accuracy. Through careful observations, computer simulations, and comparisons with external galaxies, we have learned that we inhabit one of the universe's most magnificent structures. Our galaxy spans over 100,000 light-years, contains 400 billion stars, and participates in the grandest cosmic dance imaginable. We are citizens of infinity, residents of a cosmic city beyond all human comprehension, forever seeking to understand our place in the vast architecture of creation. Tonight, as you step outside and look up at the star-filled sky, remember that you are not simply looking at distant points of light. You are seeing your cosmic neighborhood from the inside, witnessing the vast galactic home that carries you through space at speeds that dwarf all human experience. You are part of something magnificent and eternal, a passenger on a cosmic island that has traveled the universe for over 13 billion years. Every atom in your body was forged in the heart of a star that lived and died before our sun was born. You are made of star stuff, a temporary arrangement of cosmic materials that achieved consciousness and began to contemplate its own origins. This is your home. This is your story. This is your place in the cosmos, and it is more beautiful, more vast, and more extraordinary than any human mind can fully grasp.